Hi, Dalen Zartman, Ross Baker, and Matt Bowman here with Rescue Methods. We're joined by Tim Schott today with Rescue Tech Tools. We're going to go over some systematic progressions about lifting, stabilization, as well as some really neat innovations about some new products that can capture progress, help you do your lifts and stabilization applications in a much safer way and a much more efficient way. Make sure that you check out Fire Rescue One's article for this month on the lifting and stabilization components if you haven't already, so that you can correlate some of that specific information with some of these detailed tutorials and instructional periods that we're going to cover in this video series. Okay, so when we get ready to deal with stabilization and lifting, we're always going to start with that stabilization aspect. Even if we're not progressing to lifting and we're just going to use that stabilization as our platform for our extrication operations, we always want to initialize things with 4 points of contact. When we apply those points of contact, we want to try and have the forethought to keep them out of the extrication zones so that we ensure that our stabilization points aren't going to interfere with any products on the vehicle or parts of the vehicle that we're going to peel away or push away from our victim to afford that extrication. When applying these components, there's a lot of things out on the market. You can use traditional cribbing, you can use homemade stair blocks or step chocks, or you can progress to manufactured components. Today we're going to focus on Rescue Tech's product line of modular composite cribbing. It's recycled plastic components. Tim's going to give us some detailed information about each of these pieces, and we're going to go through them one at a time and talk about what the applications are for those pieces. So we're going to start up here on top with this wedge. Tim, tell us a little bit about this wedge.
Well, the wedge basically is designed to counter work with every other piece of the composite cribbing. When we start out just as a standard wedge, you have about a ½ inch increment that we can work with. As you can see, it's offset, so that at any point in time when you stick it in, you'll be able to get some sort of a capture on either the structure or the body that you're working on itself. The bottom of it also, if you invert the actual piece of cribbing, you'll notice that it also has ridge rails, so that at the point if we're working on another piece of the composite, it also has the same match rib rail, so that it can be locked into place once some force is applied to it.
Okay. Tell me a little bit about these, the rapid stairs.
The rapid stair was designed similar to the standard stair step that started out in the industry, except we did the same thing. We offset about a ½ inch on each locking tooth, so that it allows you for that quick rapid stabilization to just slide it in underneath one of the posts, capture the load, and continue your extrication.
Okay. Well, what about this segment here?
This is what we call the sliding block. What it actually does is if you place it on top of the actual rapid stair, it allows you to level out the playing surface so that you're going to make good surface contact. If you need more surface contact, instead of having just an edge load, you'll have more of a platform style load, and that'll distribute the load more evenly to the ground, allowing you to apply more force to the actual cribbing and be able to withstand the load.
Okay. Well, what about the 600 blocks here?
The 600 blocks are kind of like the big boy blocks, like Legos. We can build them up into different heights and sizes of width so that we can interlock the whole system into the actual 600 block, making ourselves a bus step chalk, if you will, if you need to, or building yourself a stack of 4x4 box cribbing.
Okay. I know for us there are a lot of unique applications with the composite cribbing. We're going to go through each of these components, how we utilize them, what we found about them out in the field, and how effective and safe they are in applying really significant loads. So one of the things that I'm a big advocate or fan of about the composite cribbing is the load design and the capacity of this cribbing. So Tim, give us a little overview on what the load capacity is on these based on these square segments.
Well, basically on the square segment, if we were to look at the wedge, when we encompass the actual surface contact of a wedge or a block, we're actually at a 50,000 pound crush rating, because it is a high pressure injection mold, not just a poured mold.
So if we built a solid base and had complete points of contact at each one of these square junctions, what would our overall load capacity be on this?
You should be able to support about 150,000 pounds.
So that's tremendous. That radically exceeds what we're typically capable of with timber cribbing. The other big thing that I'm an advocate of or a fan of with this type of composite cribbing is the lock-in elements that Tim already discussed. So all of these parts and pieces are designed to interchange with one another to afford articulating planes for more advanced lifts. For example, on cement drums, on concrete trucks or cement trucks, we can capture some of those planes when vehicles come to rest in weird positions or have unique design features, create good surface marriages between these components or lifting components on top of these components, and do much safer and more effective operations. All right, so we're ready to establish some of this now and see how it actually works in application. So for this first evolution, we're going to utilize a vehicle that's on 4 wheels. Depending on the presentation of the vehicle, those initial 4 points of contact are always going to change a little bit regarding which type of piece you utilize as well as where you place it. For the vehicle on our 4 wheels, we're typically going to stay inside of the wheel well base. If you extend outside of the wheel, if you look behind Tim right here real quick where the bumper is skinned out back here, you can see that the height level of the structural material of the vehicle is really increased. Additionally, this trunk space or cargo area has very little structural integrity until you get back towards the frame rails. So we typically want to avoid the actual rear or nose of the vehicle as some of those primary points of contact. We want to stay up in these areas, ensure that we push those points out as far as we can so that we don't interfere with our removal of our door systems. We're going to do 2 applications here. The first one is we're just going to apply a straight wedge or a rapid stair. The second application is we're going to apply a rapid stair with the sliding element on top. We're going to talk about how both those work and how taking a little time to maybe put the sliding block in initially is going to really facilitate things later on, especially if you progress towards a lift. So to place these in, it's typically a 2-man quick job. We're going to have one guy get in the wheel well, turn his back to the vehicle, grab that wheel well, and give just a short little lift. You want to make sure that you do that gradually, because remember that we're trying to create slow and stable movements for our patient as well as control of the overall load of the vehicle while we're getting ready to get into those extrication operations. So Tim, if you would go ahead and get in the wheel well there, give me a lift. We're going to take this rapid stair, we're going to slide it under, and we're going to see immediately that it just barely makes contact. You can see that in this application, we've gained what we're looking for, which is some basic stabilization, but it's pretty short-sighted because we've maxed out the capability of that rapid stair. Here's one of the great features of the composite cribbing is we can quickly do build-ups, establish those building block components away from the load, and then slide them in or move them out. We could manipulate them however we want, and they're going to stay intact because of those lock-in components with the knobs and the receiving holes. So Tim, go ahead and lift up again, and we're going to put a 600 underneath there and show how these marry up. We slide this out. We come in with our 600 block. We establish that as an elevated base platform for the rapid stair. Place the rapid stair on top, and you can see that it locks in place. Now when we go to lift, we have elevated height. I can easily slide that in, and now when he sets down, we have a lot more versatility to manipulate this to capture progress if we get into a situation where we have to lift the vehicle or further manipulate the load to accommodate other extrication applications. So that's utilizing a 600 or a base block in conjunction with the rapid stair. On this side, we're going to build that same build up with the 600 block, but we're going to use the sliding component to capture the progress, and rather than just giving us that one narrow point on the edge of the rocker that's contacting the stabilization base, we're going to create a flat platform which is going to assume or absorb more load and have better surface contact. So Tim, let's apply the same thing up here. I'll lift the vehicle this time if you want to do the 600 block, and then we'll go through that slider. A. So again, everything stays intact. Nothing falls apart when we go to advance it. When Tim's ready, he pushes that sliding block all the way down. He'll let me know when he's ready to lift.
Okay.
He slides it under, and now he can pull back on that slider until he's got a good contact point. You can see in this application now we have a flat platform underneath the base of that rocker or that lateral frame rail if it's pushed out far enough. Now, the great thing about the sliders is you have two basic applications for capturing progress when we get into lifting operations. If we're lifting from this side and we're utilizing a straight rapid stair or a stair chalk or step chalk type application, we have to advance those components further in towards the vehicle to gain elevation and capture progress. With the slider, as the vehicle raises, although we are advancing this in slightly, we are pulling back in opposition with the sliding element itself and maintaining that full surface contact as the load elevates. So having this in place initially can help streamline some of those applications for capturing progress when you get into lifting down the road. Okay, so we've applied our vertical stabilization to the platform on all 4 points going around both sides of the vehicle. We also want to make sure that we capture the forward or the lateral progress of the vehicle. We can accomplish that really quickly with the small wedges in the composite cribbing cache. Tim, what have you found about different applications with these wedges and how we can apply them to accomplish that?
You know, depending on the area and the rescuer and the size of the actual tire that you're trying to capture, sometimes we'll actually place the wedge in with the articulated plane into the tire, which will let it actually capture it, but at the same time there is some thought that it could actually roll up the inclined plane also. So depending on the tire size, we may actually turn the wedge sideways or completely, 180 degrees and capture it at the back square side of the actual cribbing point.
So based on what you discussed, Tim, and looking at these size tires, what would be your recommended application for the small wedge to capture lateral movement on that?
With this side of tires, a lot of times I'll either come in and use the square side to actually capture it and give it a nice block area, or I'll come in even at the side and catch it halfway up on the side of the groove to where I can drive it in, especially if I don't want to have any movement whatsoever. If it's winter time and you have a lot of snow, you may actually want to invert the wedge and use the more aggressive side at the bottom so that it digs in instead of pushing out. One of the things that we were showing in sandy conditions as well.
Great point. So we're going to take these small wedges, we're going to use the applications that Tim just described, and we're going to capture the aft side or the rear portion of the rear tire, the front portion of the front tire, getting all 4 wheels and tires, making sure that we've got lateral stabilization achieved. This can get a little confusing to people, at least this theology that we convey, because we're talking about points of contact again, but the number changes because the application changes. So we'll refer to this whole sequence of events that we just went through as our primary stabilization. The other elements that fall into primary stabilization are stabilization of all the other hazards of the environment and the vehicle. So remember that we've already negated the 12-volt battery or low voltage energy system. If it's a hybrid, we've taken care of the high voltage energy system. We've also ensured that the vehicle is in park, the keys are removed, and then we've evaluated the general environment. Do we have any fuel spills? Is the environment flammable or combustible? Are there any other utility-based hazards? Once all that basic primary stabilization is done, we're ready to look at secondary stabilization, which is going to typically revolve around either precariously placed vehicles or loads that we want to lift. So when we're thinking about lifting concepts, we want to analyze things from a 3-point lifting perspective as opposed to a 4-point of contact type of concept. With 3 points of contact, what we're going to visualize is using 1 point as a lifting point and then hopefully 2 points as stabilization points. Each of those points should formulate a triangle to give you effective engineering. Now understand that that is the minimum concept. We can exceed it and go to 4 or go more dramatically depending on the type of vehicle, for example, level 2 vehicles. But with most passenger vehicles, 3 points are going to get us through that equation. To demonstrate this, we're going to do a B-post or a B-pillar lift. So we're going to use this single point as our lifting point. We're going to utilize the 2 points of contact on the opposite side, which are our rapid stairs, which have captured that lateral portion of the vehicle vertically, as our other 2 points of contact. If we look at how that formulates, we're formulating that engineered triangle where we've got 2 points for stabilization laterally this way, as well as vertically this way, and 1 good lift point. When we get into lifting, we want to encourage you to follow a basic chain of events or a sequential plan for your lifting operations. We're big advocates of starting simple and progressing towards more invasive or more complex applications. When we're talking about simplicity and building up from that point, we convey this progression. So we're always going to start with a wedge lift. Because we're already applying wedges and they're already in place, we can, in theory, drive these wedges or progress these wedges towards the vehicle, providing lift. If we had an individual trapped under this vehicle, it was a pedestrian struck, something along those lines, a lot of times we may only need a couple of inches of lift to gain access to that victim and free them up. Tim, how have you guys found, regardless of our perspective and what we've utilized, what have you found out in the field with your rapid stairs as far as how they progress into the load in a driving wedge lifting application?
You can actually do that, and it can be effective. The one thing that we have found, which is one of the downfalls, is every half an inch increment seems to actually catch the load at the same time, not wanting it to move. So as you do drive it in, it takes a little more force than what you would see, let's say, with the 4x4 wedge, which has a smooth surface contact. So it's going to be a little more difficult, but it's still going to give you that advantage over the mechanics.
Great. So we've got our rapid stair and our 600 assembled together. You see again, they're staying nice and compact together. They don't fall apart. If you're going to use this wedge lift application, single lift point here, 2 capture points on the other side, you need to be cognizant of the fact that this is kind of a rapid down and dirty application. As you're driving this into the load, you're applying a lot of lateral force to the load as well as some jerky vertical lift to the load. This may not be an appropriate lifting application for all scenarios. So just keep that in mind before you start to progress down that path. One of the nice things about utilizing the wedge lift is that it's basically capturing progress as you develop into the lift. If you want to gain additional progress capture as this drives, you've already got your 2 other points established on the side of the vehicle so that this won't convert into a potential seesaw, and you can go ahead and advance your other progress capture components to make sure you're maintaining the load. Keep in mind though that if we're using the 3 points of contact lifting theory, that triangle should be adequate to effectively stabilize most of your loads without putting additional capture progress points in place. All right, so we're going to advance this right under the B. Once it's in position, we're going to go ahead and drive. You can see that we have freed up our rapid stair components. You're going to gain minimal lift out of this. Like Tim discussed, the teeth help lock in the load as you're driving the product in. So as you would continue to strike, it's going to continue to advance. But the nice thing about it is, even though it's not advancing as easily as a large timber-based wedge would or a smooth surface wedge, you don't have to worry as much about kick out or about that load sliding out if the load gets repressurized. So that's an application or an example of our wedge lift. All right, the second step in your lifting progression can be a lever lift. When we're applying levers, we're typically going to apply them as Class 1 or Class 2 lever applications. Now, it's imperative that you're capturing progress with your other progress capture components or points of contact when doing a lever lift, because more times than not out in the field, we're typically utilizing things that aren't necessarily designed to be levers. Or we're utilizing products that the lateral strength of those products is somewhat unknown. When we're dealing with passenger vehicles, the loads are typically light enough that we don't have to get real in-depth on load calculations regarding the products that we're utilizing. So in this application, we're going to use some solid timber-based dimensional timber. We're going to apply it initially utilizing a fulcrum and a lever that slides over the fulcrum, applying downward force to the backside of the lever and accomplishing lift. As I lift, Tim is going to capture the progress that I gain by advancing the rapid stairs or pulling back on the slider. So we apply it in, make sure that you get that fulcrum close to the load of the vehicle. As that fulcrum slides back, I lose more and more of the actual application of leverage that I can apply to the vehicle. So once you get it in place and you figure out how far you want to get under the rocker or under the base of the vehicle, advance that fulcrum up until it makes contact with the lever. Once you're in position, you're then ready to apply downward force. You ready, Tim?
Yes, sir.
So I apply downward force, up comes the load, Tim captures that progress. We can do it again on the other side. Up comes the load. Progress is captured. That's the first example of a lever application. The Class 2 lever mimics a wheelbarrow type of lever application. So in this application, we're going to advance the lever directly under the vehicle, and instead of applying downward force to the lever, we're going to apply upward force to the lever. So we're utilizing the ground as our fulcrum or stabilization point. The load is at the midpoint of the lever. You ready, Tim?
Yes, sir.
Use your knees, keep your back straight, give it a lift, capture progress. We'll do it again on the other side. You ready, Tim?
Yes, sir.
Give it a lift, capture progress. Utilizing mechanical components. You can see I'm one individual, and we gained a significant degree of lift just by applying a simple, well thought out mechanical lever application. If you have the available manpower in your lifting application, you're always going to be more effective if you have able bodies at each progress capture component as well as lever components. So keep in mind that if you have the access to multiple levers and multiple individuals to apply those levers, that may be a really, really fast and effective lift where you're going to gain a ton of progress, capture that progress, do it safely and effectively with some very, very simple implements. Our next step in the progression is a hydraulic lift, so we can utilize our hydraulic spreaders to lift the load using that same three-point principle. The single point being the lift point again at the B-pillar here. One of the things to discuss is the orientation of the base or the buildup of the cribbing that we utilize for that hydraulic spreader. We've got two basic options where we can either turn this parallel with the vehicle and run our spreaders perpendicular to that base, or we can run our base layer parallel with the tool so that it's perpendicular to the vehicle. If we run it perpendicular to the tool, one of the things that it affords us is less rotation or rocking on that base cribbing. If we turn these laterally sometimes, when we start to spread, the spreaders have a tendency to want to articulate down or articulate up. They'll be putting force maybe not in the center mass point of the cribbing, and if they're off to the front side or the back side of that lateral spreader cribbing, they can cause it to rotate. When we put it in line, we negate some of that application, because if the tool articulates, it's going to come down, contact the cribbing, and we've got a lot more surface contact to ground that is in load with the lift as well as the rotational forces it may be applying to the base crib. So before we get into this application, Tim, is there any considerations that you've picked up along the way about utilizing hydraulic spreaders to lift loads?
Sure. A lot of times what we find is if you're using a combi tool, a lot of times you want to use it parallel. Your cribbing will be parallel to the vehicle because the combi tool has a very small purchase tip. But when using a large spreader, such as the one we're going to use this morning, it actually has a long, narrow tip on it so that it actually is designed for new car technology. We may want to use it perpendicular to the car so that we spread out and get more points of contact with the tip, keeping the load a lot more secure as we lift it.
Great. Any other considerations that you've seen about spreaders and how they may react with loads when we're trying to lift?
One of the big things as you covered is to get that base build up, because with the spreader, the higher you go, the less safety factor you have, and you use less surface contact with the tips, allowing it to rock one way or the other and lose that load. And at the same time, when that tip rises, it has less surface contact on the unibody structure and may puncture through and not have enough surface to actually hold the load anymore. So the big thing to focus on is come up a little bit at a time, replace and build your block a little higher, and keep that lift at a minimum.
Okay. One of the last considerations that we're very passionate about is the application or the tool operation with hydraulics and pneumatic type tools. When we're utilizing them to lift loads, we want to do everything in very short, controlled bursts. Lifting with a hydraulic spreader is extremely precarious because the spreader, if you develop any inertia or momentum in the load, laterally speaking, the spreaders can very quickly and easily rock over or rotate over and catastrophically dump the load if we haven't effectively captured progress. So doing a continuous lift or a really rapid lift can sometimes facilitate that inertia or that movement development. Make sure that your operation speed is done in very, very short controlled bursts with progress capture being gained as that lift is procured. So I'm going to step over here to the progress capture point. Tim's going to run the spreader, and Matt and I are going to make sure we gain progress.
Ready?
Yes. Good. So if Tim lets the load down now, you can see that we've effectively gained what we need to base layer wise with our supporting elements or our cribbing. We've captured all that progress. We had a very safe, very fast, and very effective load lift. One of the other things I really like about the extended tips is that it allows us to create that base out here away from the vehicle where the contact point is really removed from the plane and get some very significant extension still, hopefully to the frame rail or the more structural elements of the vehicle to afford that lift. Those thin tips buy you a lot of that extra space. After hydraulic spreading applications, we're then going to look at hydraulic, pneumatic, or mechanical extended element applications. We're talking about struts. In vehicles that are on all four wheels on a stable platform like this, struts don't have an application per se. It would take a very, very small strut to be able to gain access to the wheel well components or something along those lines. You can wrap chains under underbodies and use mechanical struts to lift those components, but more times than not in a vehicle that's on four wheels, we're going to bypass that strut step in the progression and go right into airbag operations once we've gone through our wedge and lever applications. So in this component here, we're going to take our airbags. You always want to try and use stacked airbags just to give yourself a lot of versatility and maximize your potential lift. Never sell yourself short by assuming that you're only going to capture 2 inches or 4 inches. Always build out on the side of giving yourself options. Create a base layer underneath your airbags and then advance your airbags until the center point of the bag is in line with the center point of your lift. Now, when lifting with airbags, again, we're utilizing that 3-point theology. So we still have our 2 capture points on the opposite side of the vehicle. Those are giving us our stability for vertical stability as well as lateral stability. We're doing our single lift point on this side at the B post. So we're going to advance that airbag in. Once that airbag is in center mass location for a structural element under the vehicle, we're ready to lift. Now, different airbags have different specifications, not just about load capacity, but also about design and protection. These airbags, we're going to get a lot more in depth in here in just a little bit, but these airbags do not require you to use mat jacks or any type of protective sheath around the top side of the bag because of the design and the engineering behind them, as well as the rigidity of the integrated load plate that's on top of the bag. So you can go straight bags in this application. Notice we've got the 2 color-coded hoses so that we can easily identify which airbag we want lifted, and we're ready to commence with our lift. With pneumatics and hydraulics, just like we discussed before, we don't want a continuous flow of air. We want short bursts to ensure that with those short, minimal control bursts, each guy operating the progress capture components can keep up with the lift as well as make sure that we don't cause any momentum or inertia shifts within the load. Tim, are there any other specifics in general about applying airbags and any other tidbits of information that you would want to convey?
I think you covered it pretty well.
Okay, the only other big thing that we want to avoid is the kick-out zone. So when we're lifting, especially with standard pillow airbags, they're going to marry up with each other as that load articulates. And the kick-out zone is basically the area where those airbags can potentially be launched out from underneath the load. We want to make sure that we clear all personnel out from that area to ensure that we have safe operations and nobody's going to get hit by a projectile airbag. Okay, Matt, you ready to lift?
Yes, sir.
Okay, Tim, go ahead and give him the commands that you would for lifting sequence on your airbags, and let's go ahead and get this load up.
All right, unlike the standard pillows that we have out there for use, in this system, as you talked about the articulating point or the arc movement of the lift, it doesn't lift straight up in the air, so the vehicle is going to fall away from us as it lifts. So we lift with our top bag first so it stays married, if you will, to the vehicle and follows that arc movement, and then we'll go to the bottom bag to finish the lift out if needed.
Okay, great.
So let's go up on red. Up
Ready
on
to
red.
capture movement?
Ready.
Red.
Up on yellow.
Up on yellow.
Hold.
Stop.
I'm maxed out on cribbing.
Okay. Okay, once we've got the load in position, we've captured our progress, we've effected whatever rescue it is that needs to take place underneath. When we bring down these loads, it's just as imperative that we follow safe practices and ensure that we're capturing that progress as the load descends. So we always want to stay just ahead of the load with our cribbing so that if we have a failure of the airbags or something along those lines, whatever our lifting implement is, we've got components in place that will capture that load and not have a catastrophic dropping of the load or a sudden dropping of the load. So Tim, is there any other specifics that you guys utilize about bringing the loads back down?
A lot of times if we're going to follow the load down with the sliding wedge, as it's designed to increase in height and lock in place. It's not designed to follow the load down because we don't come down and rescue. We typically lock in place until the extrication is completed. Now, one thing that we do recommend was if you can take over with just a rapid stair as an incline, follow it down with the incline. Once you can remove the actual sliding wedge and stair, take it out of play and follow it down with an incline. That way you can keep that close contact and catch the load if anything goes wrong.
Great, so we're going to get rid of our travelers. We're going to go ahead and just put in some rapid stairs. And then once the load comes up a little bit and we can take the pressure off of our traveling stairs, then we'll remove them out of the equation and we'll bring the load down, staying just ahead of it with rapid stairs. Okay, here we're utilizing a level 2 vehicle to demonstrate the applications and the theologies behind struts, how we're going to utilize some struts and some basic principles about margins for those. Just like we use that 3-point principle with lifting concepts, we want to try and use that 3-point principle on the bases or the attachments of our struts as well. So when we're using struts, number one, throw them into the load in such a manner that they're going to bisect the planes or the angles of the load. So on a tractor trailer, on a vehicle, our most optimal placement for a single strut on what is to go to the corners and bisect these two planes. When we can bisect those two planes, we find that perfect marriage of lateral support and stabilization this way as well as this way. Now, we also want to make sure that we've got it thrown appropriately so that it follows that line of theology as well as vertical support. As we get that strut more and more true vertical, it becomes stronger and stronger, but it also becomes less and less stable. So the perfect balance on the angle of throw of the strut vertically, not laterally, is 30 to 45 degrees. When we start to get into that 45-degree range, we're really pushing the lateral forces that we're applying and as well transferring down to the load plate. The more lateral the strut is, the more load we're putting on our ratchet straps or our chain assemblies, as well as the more push that we're potentially applying to the load when using mechanical struts or struts with a pneumatic reserve in them. So regardless of what type of struts these are in this application, those are some general theologies that I would say are pretty good to follow. Would you agree, Tim?
Absolutely.
So follow those principles of 30 to 45 degrees, try and bisect angles. Now, if you don't have good capture points for the heads of your struts at the corners like we do in this scenario, you may need to add elements. If we were to just put struts on the back side of the truck here in line with the parallel plane of the trailer, we have no affordability of lateral stabilization. So as we lift, this vehicle could very easily shift to one side or the other. So what we've done in this application, it was actually used 2 strut components. We've put these struts in on the rear of the truck in a mechanical application, and we put the struts on the side of the truck in a lateral application, or a pneumatic application, I'm sorry. When we pneumatically use struts, the only strut that really successfully or effectively does this in unison with the airbag system is the Rescue Tech struts when deployed as part of that overall octopus system. Tim, tell us a little bit about that and how that works.
Well, one of the nice things about it is, number one, the rating. Anytime we're dealing with what we call heavy rescue, you need to know your weakest link in the system. The strut itself is rated at 15 tons at a 4-to-1 safety factor. So we know if we're going to be working on a standard load, it should be no more than 80,000 pounds. If we're only picking half that, we're picking 40,000 pounds. So knowing that weak link in your system, whether it's the strap and it needs to be a chain, those things are very important. The nice thing about the way this strut is designed, it is a mechanically locking mechanism. It automatically locks. So if you're using it in the manual version, as we are at the rear here, we'll just extend it. Every 1/25th of an inch that the strut extends, it automatically locks. There are no pins, no T-valves, no screw threads, no acne threads to deal with. It is an automatic manual locking system that's done mechanically. So every 1/25th of an inch that you extend it, it already captures the load. Now, to add to that, never before have we been able to remotely follow the load as we're going to do on the horizontal plane. With the horizontal plane, we've added air into the strut and charged it. Once it's secured, locked into place, we've charged the strut with some air up to about 30 pounds. And as we start to lift with the bags, the horizontal struts will actually extend on their own from the air pressure, but still automatically, mechanically locking every 1/25th of an inch. So we won't have to have any manpower around that strut.
That's great. An important thing with selecting struts, whatever strut you go with for your organization, you want to choose a strut that's simplistic, that's quick to deploy, and gives you versatility. Those are some great things about the Rescue Tech struts is they provide or afford all of those variables, whether you're using them mechanically, pneumatically, chasing the load, supporting the load, or helping support in the lifting operation. It's important to denote that we're never going to lift the load pneumatically with the struts. The lift is going to be accomplished with the airbags. That reserve of air is just enough in the struts to help them chase the load and maintain positive contact with the load. Some other key important facets to point out with this application is we've got these struts on the rear, we got the struts on the side. Our ratchet assemblies have gone from ground to pivot point. So if we go back to that 3 lifting point theology or theory, you can see that everything's kind of done in 3s, whether it's the triangulation of the ratchet straps, whether it's the lifting point with 2 capture points on the outside with the 5th wheel, or that component of the trailer being the other stabilization or pivot point. We've oriented everything utilizing that 3-point theology so that we have sound engineering throughout our lift. Tim, tell us a little bit. I noticed here on our cribbing, Matt's elected to put a load plate or power plate on the bottom and top of the airbags. I know that can help do some load distribution stuff, but one of the unique things I really like about it is how it locks in to those knobs on the cribbing and prevents those things from shifting. Expound on that a little bit and tell us about that.
Absolutely. The power plate itself was designed to receive the actual cribbing block, the Lego style, and lock itself in many different positions. So when you're building a base and working off of a platform, you're going to be able to lock it in so that as that arc movement takes over, the force of pushing that bag out of the actual lift is going to be limited because we're locked down and pushing that plate down into the cribbing itself and locking it in place.
Great. Okay, Tim, I'm going to go ahead and mine this one if you want to mine that one, and you can go ahead and give the sequence and we'll start lifting.
We're going to go up on yellow to make contact. Up on yellow, freeze. Now what you'll see is we've made good contact. We've actually started the lift. So now as we go up, we'll manually extend the struts and they'll capture the load where the air struts on the outside will actually do the job automatically. All right, we're going to shift to the bottom bag now and then go up on red. Freeze. Down on yellow.
Now, Tim, one of the other features about the Octopus system that I'm a really big advocate of is the fact that we can also take the load down without having people in the hazard zone or at the load. So in the pneumatic strut application in conjunction with the pneumatic airbags, when we get ready to come down, we can just dump the air through the systems, progress down with the airbags, and the struts will actually progress down with the load. But if at any point in time we disengage anything or let off of the dumps, they'll self-lock at that 1/25th of an inch and assume the load, correct?
Absolutely. What happens is the air pressure stays in the strut that is extending it and just following the load. What we end up doing with our second air line that goes to it, we have a controller in the system, is we actually hold a button, the red button, for actually unlocking the locking mechanism. It holds the locking mechanism open, so that allows us to hold it open while we're coming down. Anytime that something would go wrong and the man running the controls would release the locking button, it goes right back to locking the load and chasing the load again.
So that's an important feature regardless of the strut you're using. Remember, just like we've talked about in the other lifting application, when you're bringing the load down, it's got to be done in a controlled manner with as many safety margins and measures as you can have in place. Okay, so we're ready to bring this load down. You can see we've removed the mechanical components that were giving us that redundant safety of support from the backside. We've got our lateral stabilizations in place for our 2 points of contact there. Pivot point to the axle, pivot point to the fifth wheel, airbags are in place. We're going to inflate the airbags so that those pneumatic struts travel 1/25th of an inch, disengaging that locking mechanism, and then we're going to bring the whole load down. You'll see the struts just progress down, capturing progress as they go. Go ahead, Tim.